On December 3, 1984, 42 tons of a highly reactive chemical called methyl isocyanate escaped from a pesticide manufacturing plant in India. The resulting release remains the deadliest industrial disaster in recorded history. The Union Carbide facility was positioned immediately adjacent to a dense urban center. Only a railway line separated the volatile chemical process from residential neighborhoods. The immediate exposure to the toxic gas killed roughly 2,500 people within hours. Over the following decades, complications from the exposure drove the total casualty count as high as 20,000. Popular accounts often describe this event as a sudden, unpredictable explosion. Engineering analysis tells a different story. This was a highly preventable mechanical failure. The release was a textbook cascade failure. It was the result of a systematic erosion in process safety management, where multiple independent layers of redundant defense were defeated one by one. This chart from the Loss Prevention Bulletin documents that exact sequence. It maps the technical and managerial breakdowns that allowed the gas to escape. The investigation groups the errors into 4 distinct categories: knowledge and competence, engineering and design, systems and procedures, and overall safety culture. The initial error occurred through the failure to conduct a rigorous process hazard analysis. By placing the plant inside a population center without regular risk reviews, the facility operated on a knife edge. Because methyl isocyanate is twice as dense as air, a leak would pool at ground level, directly where tens of thousands of people lived and slept. To understand exactly how those 42 tons of chemical breached containment, we have to follow this flowchart downwards, tracing the physical path of the failure. Maintaining a chemical plant requires navigating a labyrinth of interconnected pipes, valves, and vessels. Operators initiated routine maintenance, washing pipes to flush a filter. The water encountered a blocked overflow device. Unable to drain, the flow reversed into the vent system, breached a leaking isolation valve, and moved deep into the main piping network. This water should have been stopped by a physical barrier. Operators are strictly required to install a slip blind, a solid metal plate inserted between pipe flanges to create an impenetrable seal, but the operators failed to install it. This omission should have been caught by a pre-startup safety review, or PSSR. A properly executed PSSR verifies that physical isolations are secure before water is turned on. Because this protocol was bypassed, the water flowed unchecked. A routine, low-risk pipe wash became the fatal trigger simply because essential procedural checks and physical seals were ignored. Water traveled through hundreds of meters of pipe to an unintended destination, storage tank E610, holding the methyl isocyanate inventory. Tank E610 was supposed to be pressurized with inert gas, but a leaky valve depressurized the vessel, allowing water in. Methyl isocyanate is highly reactive. Mixing it with water initiates an immediate, severe exothermic reaction, generating massive amounts of heat. As the reaction escalated, the control room operators were completely blind to the danger. When the pressure gauges on the tank began to spike, the operators ignored the readings, assuming the instruments were broken. This reflects a total collapse of the plant's asset integrity programs. Failing to maintain, inspect, and calibrate critical monitoring equipment violates basic engineering protocols. The chemical reaction inside the vessel was now accelerating in a data vacuum. Treating pressure spikes as phantom errors effectively neutralized the final layer of human intervention. Heat inside the tank accelerated the reaction further, triggering a thermal runaway. Temperatures and pressures increased on a steep exponential curve. The primary defense against a runaway is an external cooling system, but the refrigeration unit was permanently switched off to reduce costs. Without cooling, containment was lost. The hot, expanding vapor burst through the tank's relief system and vents into the stack. 3 final safety systems were designed to catch the gas before it reached the atmosphere. First, the vent gas scrubber, intended to neutralize toxic exhaust with a chemical wash, was down for maintenance. Second, the flare system, built to burn off excess gas, had been physically disconnected from the plant. Finally, the site's water curtains were activated to knock the vapor out of the air. However, the water pressure could only shoot 10 meters high. The gas was escaping from a stack 30 meters in the air. By the time the chemical reached the open atmosphere, every piece of safety hardware intended to mitigate a leak was disabled, disconnected, or under-designed. The physical decay of the abandoned facility mirrors the degraded safety culture that caused the disaster. The disaster demonstrates the inherent vulnerability of relying strictly on active safety hardware. Systems like scrubbers and flares provide a defense, but they remain subject to human error, deferred maintenance, and budget cuts. The modern engineering response is inherently safer design, or ISD. Rather than building complex systems to control hazards, ISD focuses on eliminating the hazard at the source. Applying the ISD principle of minimize, the plant should never have stored 42 tons of a highly toxic intermediate in massive concentrated tanks. Dividing the inventory into much smaller, isolated units restricts the maximum possible release size. Applying the principle of substitute, engineers could have used an entirely different chemical pathway. Reacting alpha-naphthol and phosgene first produces the final pesticide product without ever generating the volatile methyl isocyanate intermediate in the first place. True safety cannot be bolted onto a dangerous process as an afterthought. It must be engineered directly into the chemistry itself.